In the earlier lectures, you have learnt about different search techniques, game theory and other aspects of artificial intelligence. Now, one of the most important aspects of any artificial intelligence activity is how to represent knowledge, that is knowledge representation. And one of the major techniques of knowledge representation is logic. So, in this lecture we will be discussing about the different knowledge representation schemes. In fact, this discussion will be divided into a number of lectures, I would say, and that will together constitute a particular module which we are naming as module 4 of this lecture series. The first technique that we will be looking into is propositional logic. In the course of this lecture, we will gradually come to know about what is propositional logic and how it can help us in representing knowledge. But even before coming to the aspect of knowledge representation, let me first enumerate the objective of this lecture. This lecture will enable you to represent simple facts that we use in our day-to-day life in the language of propositional logic. In order to express anything, we need to take the help of some language, and propositional logic, in general logic, is one such language. We will see how we can represent simple facts using propositional logic, and we will see how we can interpret a propositional logic statement. Suppose that means that whenever a propositional logic statement is made, we have to understand what it means, and there is a mechanism that helps us in understanding the meaning of a propositional logic statement. Unless we understand what it means, we will not be able to work with it. For example, if somebody tells you something in a language that you do not know, you will not be able to understand it, and unless you understand it, you will not be able to act according to it. Hence, it is essential to interpret a propositional logic statement. That is the second objective of the lecture. And thirdly, we will be able to compute the meaning of a compound proposition, Okay? So, a compound proposition is essentially a collection, a particular way of collecting a number of single propositions and join them together, and that forms a compound proposition. So, in order to understand the meaning of a compound proposition, first of all we have to understand the meaning of the individual propositions, that is, we should be able to interpret a proposition, and we should also learn as to how we can integrate the individual meanings of the individual propositions to understand the whole. Now, before delving into the details of knowledge representation, first let us look at what is meant by intelligence and how is knowledge related to intelligence. There are different ways of interpreting knowledge. Philosophers, scientists, logicians have all interpreted, psychologists have all interpreted knowledge, all interpreted, gave some meaning to intelligence. Now, what is the role that knowledge plays in an intelligent behavior? Let us try to first look at it. Let us first try to address the question, does knowledge have any role at all in demonstrating intelligent behavior? I know that this is a debatable issue. For example, you may ask that, well, this boy is very intelligent, but he has never gone to school and he does not have enough knowledge, but still all of us accept that he is intelligent. But the debate remains that what really is meant by the knowledge. Is it the knowledge that we derive from formal education only? Yes, that is certainly a part. But besides that, there are different other aspects that come from day to day experience as we evolve, as any human being or animal evolves. They acquire from nature some intelligence, some knowledge, and that is somehow incorporated inside the being, and that plays a major role in displaying intelligent behavior. Sometimes that is too succinct, too intuitive, that we do not understand that knowledge exists, but still from that becomes evident from the behavior. Common sense knowledge, for example, even without any formal education, people can act according to their common sense. Instead of going into the details or debate on what is knowledge and how far we will say that okay, this is knowledge, this is intuition, etc. Let us first look at how this knowledge, in whatever form it might be, can help in displaying intelligent behavior. Here you can see that we are trying to sense something from the world. We are sensing, all right, and we have to sense the environment. As soon as we sense it, we accept that and work according to it. We make some decisions, and those decisions force us to take some actions. So, that is the action part. So, this is the loop that is executed all the time in our everyday life. Now, when this decision maker senses from the environment some event, maybe the temperature has gone up very high and we have to act accordingly, the decision maker takes the help of knowledge to decide on what to do given the environment that it has sensed, given the fact that it has derived, that it has observed. Based on that, it makes a decision, and while making the decision, the background knowledge that is either explicitly there or it is in the background. Okay? Either we can recognize that, okay, yes, there is a knowledgeable man, so he can do that, or even for a common person, that inbuilt knowledge that has come with him with evolution, in whatever form it might be, that plays a role, that tells the decision maker what to do, that may be in the biological system as such. Now, based on that, the action is taken. So, we can see from here that knowledge certainly have a role in demonstrating intelligent behavior, because if we cut this part off, then we will be able to sense, but we will not be able to say what to do. We would not be able to act properly. The fact that we act properly tells us that we have got the knowledge in some form which tells us how to act given a particular scenario in the environment. Okay? So, that is the basic background of knowledge and intelligence. Now, therefore, if we just go up one slide, now here you see that this knowledge certainly plays a very important part. Now, the question is, our decision maker, when we are planning, when we are studying artificial intelligence, our objective is to build a machine that will be able to behave like a human being, or at least demonstrate some intelligent behavior. Therefore, it is necessary for human beings, we may or may not know exactly how the knowledge has been incorporated in the brain, okay? But in order to build a machine that will act intelligently, it is mandatory that we must have a means of representing knowledge. How to represent knowledge? How to represent knowledge in a way that a machine can understand that? That is all what we are going to learn in this lecture and in the subsequent lectures in this module, knowledge representation. How can we represent knowledge in a machine? Okay. Now, in order to represent, express anything that we want to talk about, we need a language. So, just for expressing the knowledge, we also need to have a language that will be able to represent the domain knowledge. I have underlined this word domain because knowledge is not a small thing. I mean, it's very difficult to have a complete knowledge of everything. Even for a small problem solving activity, the amount of knowledge, say for example geometry, the amount of knowledge besides the theorems, the intuition that okay, this theorem can be applied at this point of time, that is also a part of knowledge. Now, all this is real vast, and hence we should try to first capture or first focus on a particular domain and try to represent the knowledge about that domain. We can only expect a machine to demonstrate an intelligent behavior when that machine is left to work in a particular environment, in a particular domain, provided we empower the machine with the relevant knowledge of that domain. So, in order to, just as let us take the example of the theorems in the case of geometry, we need a theorem just is an expression, and that takes help of the language English as well as the basic definitions, names, vocabulary of the domain geometry, right. So, we always need a language. Algebra, for example, is a language of expression. We can very succinctly express many things in an algebraic equation. Similarly, for representing knowledge, we need to represent, we need to take the help of some language. Now, one thing is that suppose there is some language that has represented some knowledge. Now, what is the use of that knowledge unless there is somebody who can take the help of this knowledge, who can understand the language in which the knowledge has been expressed and therefore can use it, the knowledge is of no significance. Hence, we must first have a language, no doubt about it, but also there must be excuse me, a method that will be able to use this knowledge. Okay. So, if we think of knowledge representation, we must think of both the things. One is a language, another is a viable method that can be executed in a machine, so that it can read the language, understand the language and act according to the knowledge that has been expressed in that language. So, this method that is used to interpret, understand, interpret knowledge in response to an environmental fact that has been sensed. Remember the earlier slide that we have talked about, that we sense from the environment. First you have to sense, and then you have to use the knowledge to act accordingly. That entire thing is clubbed in the name inference machine. So, an inference machine or inference mechanism, what it does is it reads the environment, can interpret the knowledge that has been represented in a suitable language and use that knowledge to act according to the need, and therefore can generate proper actions, which we often say, see, the machine or the object is behaving intelligently. So, in order to demonstrate intelligent behavior, specifically two things are needed. One is the language, the knowledge represented in some language, and a method to use the language. In all, we must have a very powerful inference machine that can understand the language in which knowledge has been represented. So, a knowledge representation should include both the language to represent knowledge and an inference mechanism that can use this knowledge. These two together, when defined, gives us a knowledge representation scheme. Now, whenever we talk of any language, then we talk about the grammar, some rules that the language must follow, because unless the language is grammatically well formed, grammatically correct, it will be difficult for others to understand it. We can take the example of our normal day-to-day English. If we say a wrong English statement, might be many of the people will not be able to understand it. Some may be able to apply their own knowledge and still understand it, but for a computer or for a machine the scenario is a little different, because here a machine can play with the things that it knows. It cannot as yet interpret in any particular way. So, we must stick to the grammar, the syntax of the language, so that the inference machine, which is nothing but a machine, which is a program running in a computer, will be able to understand what it says. So, the syntax is the grammar of any language, and semantics of a language is the meaning. Okay? For example, I say pen cut road. Okay? Cut is a verb, pen is a noun, and road is also a noun, but all this together does not really convey anything meaningful to you, okay? Although everything was there. I can say here I have made a syntactic mistake. I should have said, even if it is syntactically corrected, as the pen cuts the road. Now, does it really mean anything? Can you really map this to a real world scenario? Have you ever seen a pen cutting the road? So, the semantics is an issue. Does it carry the meaning? So, two things are important. One is the syntax, one is the semantics. Both of them must be well defined in order to form a knowledge representation language. For example, if we write laughs Tom. Now, laughs, then parenthesis Tom. What does it mean? Does it mean Tom laughs? Does it mean Tom is laughed at? What does it mean? There must be, assuming that this is a correct syntax in some language, what is the meaning of that? What is the semantics of this? We must understand this. For example, here likes Sunita Aditi. Now, what does it mean? Sunita likes Aditi or Aditi likes Sunita? There must be a specific interpretation that should be given in order that this statement like Sunita Aditi can qualify as a valid knowledge representation language. Okay? Now, when we are talking of language, we must search for a language, and logic is one such formal language. Okay? Propositional logic, let us start with propositional logic, because propositional logic is would say a relatively simpler form of logic. Anything that we use in our day-to-day world, in our statements, is a proposition. Say I make the statement, Anil is intelligent. It is a statement, it is a proposition. Anil is hardworking. It is another proposition. I am making a statement about Anil. Okay? Anil is hardworking. So, both of these are propositions. Okay? Now, so Anil is intelligent is a proposition, Anil is hardworking is a proposition. Again, if I make a statement like, if Anil is intelligent and Anil is hardworking, then Anil scores high marks. This is also a proposition, because I am making another statement, but you see that this statement is a combination of some other propositions. Say Anil is intelligent is a proposition, and this one says if Anil is intelligent and Anil is hardworking, this Anil is hardworking is itself a proposition here, all right. Then Anil scores high marks. So, all these white ones are also individually their propositions, but when I am connecting all these together, I am making another proposition. we will see later that this one is called a compound proposition. Okay. So, briefly speaking, whenever we speak in our day to day life, we always, whatever statements we make consists of propositions. Now, these propositions, say Anil is intelligent, Anil is hardworking, these are constituted of objects and relations or functions. Now, Anil is intelligent, I make a statement, this statement can be true, this statement can be false. Anil is hardworking, can be true, can be false. So, any proposition in propositional logic can have either of two values, true or false. Okay. Now, so and it is constituted of objects and relations or functions. So, you see Anil is an object, hardworking, intelligent, these are some functions or relations depending on your usage. And so, when we write intelligent Anil, so I am putting in some function on Anil, and that means Anil is intelligent, and this entire thing can be true if the Anil that I am talking about, is true, is intelligent. If that Anil is intelligent, then this statement is true. Hardworking Anil, again similarly Anil means Anil is hardworking. So, again these are propositions. Now, propositions can be written either in this way or intelligent Anil. In that way I could have also written, provided my language, the syntax of the language had allowed it. A proposition can be true or false, as has just now been told. Now, let us look at it a little more formally. So, can I write it in any particular way? Can I write it in any way I like? For example, Anil, intelligent Anil, or intelligent Anil within parenthesis, or what should I write? In order to know that, we must come to the syntax properly. Okay. And as I have said, the syntax basically talks about the grammar of the sentence. Now, let P stand for this proposition that I was using, intelligent Anil. Okay. Let Q stand for hardworking Anil. Now, what does P, look at this symbol, this is a logical AND. What does P and Q mean? P and Q means, so P and Q is a new proposition. Now, P and Q is true when P is true and Q is true, when both of them are true. If either of them is false, then P and Q is not true. So, but you see, P and Q is another proposition. Although P is true, Q is false, P and Q both will be false. Although P is true, when P is true and Q is true, I will have to separately evaluate P and Q and see that P and Q is true. Okay. Similarly, what does P, this symbol means P or Q. What does P or Q mean? This is again another proposition, P or Q. This means that when either P is true or Q is true, any one of them, if they are true, then this proposition P or Q will be true. So, P and Q, P or Q are examples of compound propositions, okay? Because P is a proposition statement, Q is a statement. I have formed a new statement by applying some operators, some connection operators like AND, OR, etc. We will see that there are other operators also which you can use to make more compound statements. Now, let us look at a little more formally the syntactic elements of propositional logic. Any language will have some vocabulary. For example, the language English, for that we have got the vowels, the consonants, some numbers, etc. Similarly, for propositional logic also the vocabulary is a set of propositional symbols. Now, whether Anil is intelligent, Anil is hardworking, Geeta is beautiful, Sita is smart, all these propositions we can symbolically represent each of them propositions as, say, for example, P, Q, R. So, etc. So, let us symbolically represent P, Q, R. These are set of propositional symbols. Now, there will be a set of propositional symbols, and as we have said that any proposition can be either true or false. So, each of these P, Q or R can be true or false. Besides, there will be a set of logical operations. Logical operations. Now, here I would like to highlight this logical. Logical, why do you say this is a logical operator? Logical operator because this operator can have either true value or false value. I mean, after I apply a logical operator on two variables, say P and Q. Okay, so I will get, say, P and Q, that itself will return a value true or false. So, that is the significance of logical operator. Now, we can have say and, which is, look at the symbol, or not and implies. These are the basic four operators, logical operators that are used in propositional logic. Often parenthesis is also used for grouping. There are two special symbols, true and false. Basically, these are logical constants. Time and again I was saying that time and again we are saying that any proposition can have the value true or false, and therefore, true or false, these two are two very important logical constants that we will be using all through. So, basically we have seen that there are four basic operators besides parenthesis: and, or, not and implies. Now, let us see, we will see the meaning of those, and but before that let us see how to form propositional sentences. We have got the vocabulary, which are set of propositional symbols, we have got the logical operators, and we have got the logical constants like true or false, right. So, let us see how we can form logical sentences using this. Each symbol, whatever that is, proposition is a sentence. Okay? It is always a sentence. If P is a sentence and Q is a sentence, then if we block them in parenthesis, P is a sentence. Okay? Since if P is a sentence and Q is a sentence, P and Q is a sentence. All right? P and Q is a sentence. Similarly, P or Q is a sentence. If P is a sentence, not P is also a sentence. For example, if we say Anil is good, then, and that is P, all right, then not P is not Anil is good. Now, Anil is good was true, and not of Anil is good will be false, but not of Anil is good is also a valid sentence. It may evaluate to true or may evaluate to false. P implies Q is also a sentence. Nothing else is a sentence. Now, this is a very important, that in order to qualify as a valid propositional sentence, each of these, the say P, whatever the statement that I formed, that say P is a sentence and Q is a sentence. Now, I can comply with these only in these allowed or ways. Either I block them, I bracket them in a parenthesis, then it is still a valid sentence. P and Q will be a sentence. P or Q will also be a sentence. Not P is a sentence. P implies Q is a sentence, and nothing else is a sentence. Now, this is often you will see sentences are also called well formed formulae, written in short WFF, okay, well formed formulae. Now, this is so we will use the term sentence or well formed formula interchangeably. Now, let us see now therefore, some example WFFs, well formed formulae. P, yes, there is a well formed formula. True, it is a logical constant, so it is a well formed formula. P and Q, it uses our allowed operator and, so it is a well formed formula. P or Q implies R. Let us look at this. P or Q, this is a valid proposition, and any valid proposition, say P implies R, that is a valid proposition. So, this whole thing implies R is a valid proposition. So, this is a valid sentence. P and Q or R implies S is a valid sentence. Okay. Now, not of P or Q, let us see, we can look at it in a, we can just observe here. I see that P is a proposition or a sentence, Q is a proposition or a sentence. I say write, say for example, let me go up, say P is a valid sentence, Q is a valid sentence, and therefore, P or Q is also a valid sentence. And since this is a valid sentence, if I apply the not operator over there, that is also a valid sentence. Okay. Similarly, here you see that not of P or Q implies R and S, this is also a valid sentence. Okay. Now, there is a special meaning of this implication statement that we are talking of. What does implication mean? Implication, say when we say X implies Y or P implies Q, that means if P is true, then Q is true, all right. P implies Q, then P is true, then Q is true, but not the other way around. It tells of a necessary condition. If P is true, then Q will certainly be true, but it tells of a sufficient condition, I am sorry. Okay. Say for example, if it rains, then the roads are wet. If it rains, then the roads are wet. So, it rains, that is my P, and the roads are wet, that is Q. So, if it rains, that means if it rains is true, then the roads are wet. But if we say if the roads are wet, then it rains. Now, is it an implication? Because if the roads are wet, can I always infer that it rains? Because the roads can be wet because of some other reason also. There might be a sprinkler that has been used to clean the road, or there has been, the road has been washed, it did not rain. So, roads are wet is not a sufficient condition to say that it rains. So, in the case of implication, when we write P implies Q, that means if P is true, then Q is true, but Q can be true even if P is false. Now, this is a sufficient condition, but not a necessary condition. Equivalence is a bijection, that means for example, it is a bidirectional statement. P is true, if P is true, then Q is true, and again if Q is true, then also we can infer that P is true. Now, here let us try with an example. If two sides of a triangle are equal, then two base angles of the triangle are equal. Now, we know from our knowledge of geometry, if two sides of a triangle are equal, then that is an isosceles triangle, and the base angles of an isosceles triangle are equal. So, if I had stated it in a different way, that if two base angles of the triangle are equal, then the two sides of the triangle are equal, that would be true also. So, in that case, if I say two sides of a triangle are equal, that is P, and two base angles of a triangle are equal, that is Q, then I could have said P implies Q, all right, and Q implies P. So, therefore, since the equivalence can be expressed using two sentences like P implies Q, Q implies P, in propositional logic, equivalence is not a necessary operator. we have seen that along with and, or, not, we had the implies operator, and with implies operator with two sentences giving the both directions of implication, we can capture equivalence. All right. So, we can have P implies Q and Q implies P. Next comes a very important issue. So, with this brief discussion on syntax, let us come to the semantics, the meaning of a propositional sentence. Now, when we try to understand a sentence, then essentially what we do is we interpret that sentence. We try to understand each of the propositions and try to see whether that is true or false, and then we make a decision on the whole. Now, so if there be a sentence, say P, we must first interpret what does that P mean. Anil is intelligent. Okay, what is the meaning of intelligent? What is Anil? All these are nothing but symbolic labels that we interpret in a particular world. We will discuss what this is. When we interpret a sentence in a world, in a particular world, the world can be the world of football match, the world of cricket match, the world of picnic, okay, the world of classroom. All these things are different worlds, and each of these worlds have got some known relations, some known functions, and there are some interpretations that we give in the particular world. Now, what is true in this world may not be true in another world. Okay? The rule of a baseball match is different from the rule of a cricket match. So, the cricket match, along with all its rules, all its definitions, all these things form a world. Similarly, a soccer match or a baseball match forms a different world. So, when we interpret a sentence in a world, we assign meaning to it, and that evaluates to true or false. Okay. For example, let us start with a proposition P, and suppose that proposition means a child can write. That is a proposition. So, the child this proposition P is a label for the child can write, and suppose here we have got a word nursery, and there is another word class 2. Okay. Now, when what is the truth value of this statement, the child can write? When I interpret it in this world nursery, probably it evaluates as false, because suppose the children in the nursery cannot write. But again, when I interpret it in the world of class 2, that evaluates to true. All right. So, you see the same proposition P can be interpreted in two different worlds in two different ways. Again, suppose this P is now interpreted as another statement, the child can speak. Now, the child can speak is an interpretation of P, but again that one, when I interpret the word nursery, that should evaluate to true. Again that thing, when interpreted in the world of class 2, that is true. So, you see this statement P can have value true or false depending on its interpretation. When I interpret P as the child can write, okay, and that is interpreted in the world nursery, then it evaluates to false. But when this is interpreted in the world class 2, that evaluates to true. Now, when P is interpreted to the child can speak, that can evaluate to true when interpreted in this world. Please note this statement, when interpreted in a particular world, that is very important, and this interpretation itself attributes the meaning or the semantics to the proposition. We will see a couple of more examples. Say again here, there is another example P. Now, P is Ram is intelligent. P is labeled as Ram is intelligent. and Q is another statement which is saying Geeta is diligent. All right. Now, you can say that P, there is some hidden interpretation here. P, Ram is intelligent. Which Ram I am talking about? I must be meaning some Ram which is a constant, that is subject to the way I have interpreted it. Now, say when I again look at class 2 and there is class 3, and there is a Ram in class 3 who is intelligent, then this Ram is intelligent evaluates to true, and might be Geeta is diligent, that is talking about a new proposition. Geeta is diligent is false when I talk about the Geeta who studies in class 2. All right. But Ram is intelligent, there is a Ram also in class 2. That Ram is not that intelligent. So, that evaluates to false. Similarly, Geeta is diligent, and that evaluated to true for the Geeta that was in class 2, but if I interpret for the Geeta which is in class 3, she is also intelligent. Okay. So, both of them are intelligent. Okay, fine. All right. So, you can see here. That it is very much dependent. Say we start with, we will be dealing with these two symbols P, Q. Now, whether P is true or P is false, Q is true or Q is false, that is totally dependent on the way we interpret it in a particular world. These are the two example words that we are talking of. Okay. So, how do you get the meaning ultimately? Now, please remember that sentences can be compound propositions. We have seen that P is a sentence, Q is a sentence. Now, we can connect them in different ways, and thereby we can get different compound statements, right. So, sentences can be compound propositions. For that, in order to understand the meaning of the sentence, we have to interpret each individual atomic proposition to the same world. That is important. We must interpret it in the same world. Unless we interpret it in the same world, the meaning, it will not be really meaningful, if we can say. Okay. Now, so first step is we interpret each atomic proposition in the same world and assign truth values to each interpretation, to each of the interpretations, each of the atomic interpretations. We take atomic propositions, we assign truth values to the interpretation of each of the atomic propositions and compute the truth value of the compound proposition. Okay. Sorry, I moved a little fast. So, there are three steps. We interpret each atomic proposition, assign truth values to each interpretation, and then compute the truth value of the compound proposition. All right. Now, example, say P is a proposition that is actually meaning likes Sumit Sunil. That means Sumit, my interpretation is that Sumit likes Sunil, and Q is knows Jyoti Sudhir. That means Jyoti knows Sudhir. Sumit likes Sunil. Okay, suppose that is my syntactic aspect. Now, the world that we are talking of is that Sumit and Sunil are friends and Jyoti and Sudhir are known to each other. Then what will happen? Sumit and Sunil are friends, and obviously friends like each other. So, this one will evaluate to true, and Jyoti and Sudhir are also known to each other. So, this is also true in that world, but might be Geeta and Sudhir do not know each other. So, the proposition knows Geeta Sudhir will evaluate to false, but knows Jyoti Sudhir evaluates to true. So, here we see that P evaluates to true, Q also evaluates to true. Therefore, P and Q, in this case P and Q is true, P and Q is true because both of them are correct. But what happens with P and not Q? Here you see Q was true and not of Q, that means, let us see what does not Q mean here. Knows Jyoti Sudhir. I negate that. That means does not know Jyoti Sudhir. But Jyoti and Sudhir know each other. So knows Jyoti Sudhir is true, does not know Jyoti Sudhir is false. You see that the world that we are talking about, that plays a very important role, because the truth value of this proposition would have varied depending on in the world in which you are interpreting. You can see that P and Q is true, but now not Q means that this part which was true in this world, not Q is false in that world, in the same world. So now this is false, P is true. So P and not Q is false. Okay. Now let us talk about, now we have seen the world part. Now there is a very important concept, validity of a sentence. Often we say this is valid, this is invalid, but in the case of logic, this validity is a very important notion and we must try to understand that. A propositional sentence is said to be valid if, under all possible interpretations, it is true. Okay? If a propositional sentence is true under all possible interpretations, then it is called valid. So irrespective of the world in which you interpret it, right? If the propositional sentence always evaluates to true, then it is a valid proposition. We will see later there are other definitions like satisfiability. So whenever a proposition is evaluated to true in a particular world, then that is satisfied by that world, but it is not a valid statement. When we say a particular statement is valid, then it will be true irrespective of the world in which I interpret it. Okay? Now a typical example is, say, P or not P. P or not P. Now P can be true. If P is true, then not P will be false. But we know that in an or conjunct, or connector, P or not P, in that case, if any one of them is true, it will be true. So now what will happen if P is false? If P is false, then not P will be true. So any one of them will be true. Any one of them will ultimately be true always, irrespective of whatever P means. If P means Gita is intelligent, Sita is diligent, okay, whatever interpretation you give, it does not really matter. P or not P will always be true for any particular interpretation you give in any particular world. If P be some statement from the world of cricket and not P is also computed in that particular domain, then of course P or not P, either of them will always be true, and hence this proposition will always be true. So tautology, this is known as tautology, and tautology is a classical example of a valid sentence. So once again I repeat, what is a valid sentence? A sentence that is true irrespective of interpretation. Now before going to the quiz, let me once again summarize whatever we have looked at today. We said at the very beginning that in order to represent knowledge, we have to take recourse to a particular language. That is number one. And any language, if it has to be very easily and mechanically understood, if it has to be understood by machine, then it must adhere to a strict syntax, and that syntax will be interpreted by the machine, which will understand its meaning. Okay. Now, we also said that knowledge is important in order to exhibit intelligent behavior, because whenever we sense something from the world, we have to act according to it. Now, in order to act according to it, we will have to sense it, but just merely sensing will not do. We will also have to act according to it. And how do you know how to act? For that, we will have to have some knowledge that will be accumulated and kept. Now, we may keep the knowledge in some way, but how do we know? It will not at all be useful unless we can use that knowledge. In order to use that knowledge, we need an inference mechanism which must understand the knowledge, and in order that an inference mechanism can understand it and can interpret it, it must have a strict syntax, a language structure. And we started with logic, and specifically propositional logic, which is a part of logic. All right. Now, this propositional logic has got a set of vocabulary. Each of those vocabularies can be, the vocabulary consists of some atomic statements like P, Q, R, each of which we have given examples of, right. And we can form sentence, each of them are sentences, and there are some rules using which we can form compound sentences. We can use and, or, not, implication, and using this we will make compound sentences. And the semantics of a particular sentence, may it be compound or simple, depends on its interpretation in a particular world. Okay. We have shown how to interpret it. Now, after interpretation, we will find out the truth value of that. Okay. Now, we will see in the next lecture how the actual inferencing is done in case of propositional logic. In this lecture, we have just introduced you so that you can take it up from here. In the meanwhile, it will be good to have a couple of these exercises done. So, here you see, express the following English statements in the language of propositional logic. It rains in July. Okay. The book is not costly. If it rains today and one does not carry umbrella, he will be drenched. Now, some of these will be very easy, some of them will be little difficult. We will look at it in the next lecture how to solve them. Now, you can see here, this one is a compound proposition. It will require some compound propositions, and these are simple propositions, but here again you will need some logical operators. You just find out what it is. And the second part is, if P is true and Q is true, then are the following true or false? Please note down, P implies Q. So, if P is true and Q is true, then I am asking whether this entire proposition, whether it is true or false. Not P or Q implies Q, not P or Q implies Q, not P, the third one, not P or Q implies P, P or not P implies T, T is a logical constant, true. Okay. So, please note down, we will discuss about this in the next lecture. Let's I do not know whether you have been able to take up the earlier one, also take it down. So, in the first one, what we are showing here is we want you to first translate these in the language of propositional logic. All right. So, just follow the syntax and transform them in the language of propositional logic. The second one, the book is not costly. If it rains today and one does not carry umbrella, he will be drenched. So, and the second one, second assignment, here there is a little bit of semantics that you have to look at. You have to know whether they are evaluating to true or false. We have not, I know that we have not formally discussed how to evaluate this, but I am just leaving it as an exercise. You try whether you can find or compute the truth value of these. In the next class, next lecture, we will see how it can be formally done. So much for today. Wait for that. And in the next lecture, we will be talking about the inferencing and how we automatically find the truth value of the propositional